Okay, this problem is a bit tricky, but still okay. Wheel A of radius RA equals 10 centimeters is coupled by a chain B to wheel C of radius RC equals 25 centimeters. Wheel A increases its angular speed from rest at a uniform rate of 1.60 radians per second squared. Determine the time for wheel C to reach a rotational speed of 100 revolutions per minute. First impressions of this problem is that there are two wheels, wheel A and wheel C, and somehow the first thing that comes to my mind is that we have to relate both of these wheels to somehow solve this this particular problem. And so I'm looking at the back of my mind, I'm already looking for strategies on how to relate the two. And immediately it appeared to me that these two wheels are coupled by a chain, and it dawned on me that since they are coupled, the speed of this chain is really influencing both wheels. So whatever the speed of this chain is, that would be the speed of the rotation of wheel A and wheel B. And when I'm talking of speed, I'm referring to tangential speed or tangential velocity. So what I'm saying is that the tangential velocity of A must be equal to the tangential velocity of C because they are coupled by the same chain. So that's the first thing that came to mind, that the tangential velocity of A is equal to tangential velocity of C. Now I want to expand both sides. We know that tangential velocity is related to angular velocity by the formula V equals R omega. So I'm going to expand this left side to RA omega A and this right side to RC omega C. And I am going to rearrange this formula so that it says isolates omega A on the left side of the equation. Now I have a nice formula for omega A is equal to RC omega C over RA. Why did I do this? Well, I did this because the second sentence refers to the wheel A. So wheel A increases its angular speed from rest to a uniform rate of 1.60 radians per. So I felt that this was an important part of the problem, that the angular velocity of wheel A is an important part of the problem. So that's why I derived this. Maybe I will use that later. And sure enough, I was able to use this uh, derivation. Says here in the second line that they are talking about acceleration. So I have this formula for angular acceleration. I know this might come in handy. And expanded that to omega f minus omega I over t. And now it says here, but wait a minute, I just manipulated that equation further, converted it into this. Omega f is equal to omega I plus at. This is this is one of the kinematic equations for constant acceleration. It says here that the wheel increased from rest, so omega initial is 0, and it has a uniform rate of alpha, and the t is not really given. So omega f. Okay. So this is what omega f is, this formula RC omega C over RA. So I placed it right there. So why did I substitute this to omega f? Well, this is omega A RC omega C over RA. This is the general relationship for omega of A. So I could substitute the same equation here for omega I. Maybe I can also write RC omega C over RA here, since this formula omega A is a general relationship. But we already know that omega I is 0. That's why I just substituted 0 for omega I, and for omega F I substituted this because we're talking about wheel A. For wheel A, I substituted this general formula RC omega C over RA, and since 0 man siya, so I just removed that, and now I have here, and I decided to just tag on a subscript for alpha because we're dealing with wheel A. So we determine the time for wheel C. So here we're really looking for time for wheel A, but time is the same for both. So if we get the time here, we also get the time for, right, for wheel C. We'll see about that. So now I rearranged, divided both sides by alpha A, and now we have a formula for the time. And we're asked to get the time for wheel C to reach 100 revolutions, so we substituted 100 revolutions per minute here, omega C, and we get the time 16.4 seconds. I hope you're not as confused as I am, but I think I explained it good enough. 50% okay.